As I said, we don't need to follow the US model exactly in other countries like India, but if they have done a lot of the groundwork to provide a nice framework that you can adopt to your system, then it saves a lot of time and effort and resources, right? So this is how it's imagined in this paper: simplifying NOAA's operational forecast suite, transitioning 21 of NOAA's operational forecast systems into 8 applications, right? So this is basically an engineering approach when it comes to forecasting, because different sectors need forecasts with different confidences, different lead times, and so on. So you can have multiple operational forecast systems to meet the needs, but then you have to say how the unified forecast system will work. So here you have 21 systems in NOAA's forecast suites. Goes all the way from global weather, waves, and global analysis, so GFS GDAS, down to space weather 2. So there's space weather 1 and space weather 2 in terms of forecast systems. So this is NOAA's weather to climate prediction capability developed over the last 2 decades. Often when you are going along and meeting needs of different demands that are coming either from the government or from the users and societies, you keep developing models to just meet those needs, and soon you will realize that you have a huge number of forecast systems and maybe they are not as optimally combined as they could be. So the transition over time is seen here as community modeling co-development loop, where you are merging these various things. So you have let's say private players, NOAA and academies playing roles, academia, and together they have to work together like a gear to produce the unified forecast system applications. So medium range and sub-seasonal. So you have short range 1 to 3 days, medium range 3 to 10 days, and sub-seasonal is weeks 2 to 4. Basically anything less than a season is sub-seasonal, and in each case there is predictability coming from somewhere, like the Madden-Julian oscillation at the intra-seasonal time scale, and so on. And you have marine and cryosphere demands and seasonal forecasts. So that's the community modeling co-development giving you those. You need hurricane forecast, short range, regional, high-res CAM, and regional air quality. That's the community atmospheric model. Air quality and dispersion, coastal forecasts, lakes, hydrology, and space weather. Space weather is very important. We don't think about it much, but for all the space business for NASA and also NOAA, that can be very important. So the Unified Forecast System community refers to forecast systems as forecast applications. For example, the hurricane application. In other contexts, the NWP community uses the term application to indicate a downstream product that may not be an operational product. So where the forecast is converted by somebody into forecast for health or agriculture, water, and so on. Throughout this paper, we use the word forecast application to indicate the former and product application to indicate the latter. So forecast application is just forecast systems within the UFS framework, and product application is where you translate the forecast into a sector or a user group and so on. So strategic basis for EPIC. This is a long section, but I'm going to take just the top paragraph. EPIC's vision is to enable the most accurate and reliable operational Earth system forecast model in the world. EPIC's mission is to be the catalyst for community research and modeling focused on informing and accelerating advances in our nation's operational NWP forecast modeling system. So numerical weather prediction. NOAA is evolving and expanding these forecast systems to include Earth prediction systems. Initially, EPIC's focus will be on the unified forecast system, including all model elements needed for NWP forecast production. So data assimilation, ensemble design, coupling, physical and Earth system components, and metadata protocols, tools, and algorithms to facilitate post-processing of model outputs for various product applications in this terminology. So building an open and dynamic collaboration within the earth sciences community then becomes very critical to make sure that the partnerships between academia, private, and NOAA can actually work effectively and efficiently. So you have contracted service as external, NOAA program which is internal, and EPIC is kind of an infrastructure that brings people together from different spheres. So 7 core investment areas of EPIC. The EPIC program includes both the contracted services and EPIC program office activities in NOAA's weather program office. So contracted service is pretty huge. Lots of contract workers sit within NOAA or outside based on their security clearance and other details or how the contractor works. There's always issues of paying rent and so on and so forth as well. So here is the EPIC virtual center with EPIC sitting in the middle. So you have user support, so you can start anywhere. So you have things like software engineering with software infrastructure, user support services with external engagement and community, so that you're getting constant feedbacks on the use and usability of the products, management and planning, always critical, scientific innovation where academia can continuously feed the new exciting findings to improve EPIC's mission, cloud-based high-performance computing, going back to software infrastructure and software engineering. Sounds kind of simple, but yet making sure that people don't work in silos or academia doesn't become completely disconnected from the operational forecasting systems. This is very useful. Tactical approaches. NOAA has embarked on a unified approach to its forecast systems, drawing from the seamless suite of operational deterministic and ensemble weather and seasonal UFS based prediction system that we saw already. EPIC supports NOAA's unification strategy by rolling out a single coupled modeling infrastructure with a select number of component models addressing both operational and research requirements using an optimized software architecture. A high-level view of how EPIC will accomplish its value proposition is provided in figure 4, which is here. So here, for example, the use components that are operational and research requirements means academia can actually use the unified forecast system to do their sensitivity studies, test out their ideas and so on. Otherwise it becomes impossible to bring new ideas. Usually the forecast system is right now frozen and you cannot touch it, and so trying things is difficult. So is there a way to do smart software engineering where people can do sensitivity studies and other test ideas without affecting the actual forecast, operational forecasting in any way? So UFS model and infrastructure ports to cloud service providers, user support and community engagement to accelerate innovation. So you want constant feedback from users saying your drought or heat wave forecast or extreme rainfall forecast, snowfall forecast is not as good as it should be, or whatever else, or this particular product application is doing very well, and so on. So again, just it's what is ongoing and what is future work. So you have short range weather forecasting, which is being morphed into this UFS under EPIC. Medium range weather, so these are systems that existed but now being redesigned within the EPIC framework or UFS framework. Plan scope of work for production and code integration, build cloud-based community modeling infrastructure, build EPIC community portal, and here you are providing continuous community engagement and user support. Okay, so just try to think of these as the components of EPIC and how the partnerships work. So additional assessments to expand the UFS scope beyond weather scale. So this is what is being built, and this is the future need where you would move to cryosphere, coastal and maritime, space weather, atmospheric composition, air quality, which is very important, kills a lot of people, and the productivity loss and so on are very high. Hurricanes, hydrology, subseasonal to seasonal for various sectoral applications that I mentioned already. So this is about continued development of community modeling infrastructure. So you are coming here with the what's going on to feed into future work, and adapt modeling portal as new modeling developments are implemented, so that constantly you are upgrading the system and not waiting for 2 years and seeing what is now able to be operationalized, and so on and so forth. So the scope of science and technology, research to operations, R2O or R2X funnel, indicating the progression of readiness level. So it's like technology readiness level that you may be used to, that goes from basic research, so a readiness level of 1 to 2, to high readiness for operational applications implementation, so that takes you to RL9, across the scope of the technology and the life cycle of the research, with implications for the broader scientific community, the NOAA's mission that it has to stay focused on, and continued research and development aimed at operational application. Okay, so here you have research readiness level 1 to 2, development readiness level 3 to 5, demonstration readiness level 6 to 8, and deployment at readiness level 9. So tailored requirements at this end, and you have broader community benefits evolving along the way. So increased understanding, publications, which academia always needs for its promotion and evaluation and so on, contributions to NWP, non-NOAA modeling advances, so whatever happens within academia or private sector and so on. And here is the life cycle phase of science and technology, with research and development bringing you to readiness level, let's say 5, and then transition to 6 and 8 and 9 with demonstration, evaluation, validation, and operationalization, where you are basically serving broadly relevant to NOAA's mission in terms of its readiness level to meet the demands of the mission. So that's the scope of science and technology here. Okay, so how long is this podcast? Let's try to keep them yeah, it's already over 12 minutes, so we can come back and continue. I don't know, I have just a few more slides, so maybe we'll finish in 1 or 2 more podcasts, but you get the idea that this is a well thought out process. Implementation, already some parts are going on, as we saw here in terms of weather. So here, for example, what is ongoing in terms of transitioning short range weather and medium range weather into the EPIC framework to move towards UFS, with future work focused on the sectors that are waiting to be built into the system, with this readiness levels being tracked from research to deployment. So we'll come back and continue the discussion in the next podcast on this EPIC framework for Earth prediction systems. Okay.